In the fourth presentation of linear systems, we will discuss the frequency response function, that is the path between the excitation and response, and we will show how it can be used and interpreted. So, as you know from previous presentations, we can view the frequency response function between excitation and the response as representing the path between the excitation and response. And to provide an example, first of all, how you can calculate or derive the frequency response function, and also how to interpret it. We will consider a mass spring damper system as an example. So suppose now that the input, the lower part of the spring damper system, is subject to excitation. That is, we prescribe an oscillating Z coordinate here at the input. And then the response is, of course, how the mass m is displaced, displacement x here. And this can, for example, be used as a very, very simple model of a car running over a bumpy road. So the Z here is in principle then the position of the contact point between the wheel and the road surface. And x here is of course the car body position. So the question now is how the contact point position Z here affects the car body position, car body displacement x. So if we assume linear systems, we can state that there must be a linear relationship between the car displacement and the road and the contact point position Z. And h here is the frequency response function that couples the excitation with the response. So how then can we continue here? Well, we can, to derive this frequency response function, we have to decompose the system into its components and introduce cut forces. So the cut forces here is the spring damper system force acting on the mass and its balancing force acting on top of the mass spring, of the spring damper system. And then in the contact point, since this is a massless system, we must have the same force in opposite direction in the input side here. So if we formulate the governing equations here, we first of all have the equation of motion for the mass, and then the spring damper equation. And the frequency response function, as we know from an earlier presentation, is the ratio of the complex response over the complex excitation. And in our case, of course, the response is x, the displacement x, and the excitation is the displacement z. So mathematically you can formulate it in this way, this ratio, as function of frequency. So the complex excitation, if we assume then sinusoidal time dependence here, that is in principle then a sinusoidal surface and a car running with constant speed, then we get this perfectly sinusoidal excitation. And we have the complex amplitude here, and in the same way, since it's a linear system, then we know that the response must have the same frequency content. The only thing that is changed is the complex amplitude, which contains also the phase shift between z and x. And then we introduce this into the governing equations and perform the time derivations and obtain these two equations. And if we solve for x from the first and introduce sorry, we put these two equal in order to eliminate the spring damper force, and then we can solve for the ratio of x over z, and we obtain this frequency response function for this system that connects then the excitation z and the response x. So, what is the properties now of this frequency response function? Well, first of all, you can see here that the frequency response function is a function of the system properties and the excitation angular frequency. So the size, the amplitude of the excitation is not part of this frequency response function. So it depends on the excitation frequency and the system properties, nothing else. Also, we find the imaginary unit here in two places in this case. So that means that the frequency response function is complex valued. And how can that be interpreted? That is the question. Well, first of all, the absolute value of the frequency response function, or the size of it, gives the amplification along the path. So if the absolute value of h is a number larger than 1, then we know that the amplitude of, or the peak value of x is larger than the peak value of z. Secondly, the phase angle, the phase of the frequency response function, can we show to be correspond to a time shift between the excitation and the response. So if we have a purely sinusoidal excitation, then we will get a pure sinusoidal response, but its peaks and throughs will be shifted in time relative to the excitation. And this time shift will be determined by the size of the phase angle. We will show that later on. An example now. Suppose now that the mass here is 340 kilograms and that we have a spring constant of 120 kilonewtons per meter. The viscous damping coefficient is 1.2 kilonewtons seconds per meter, and let us consider a specific excitation frequency at 3.0 Hertz. Then if we consider now the frequency response function at this particular frequency, then we can start with the amplification from the excitation to the response, that is the absolute value. If we introduce the parameters and calculates the absolute value, we will find that it is 5.4 meters over meters, which is the unit in this case. And the phase angle, the phase shift, phi here, if we, well, the phase of a ratio between two complex numbers is the difference between the phase angles of the numerator and the denominator, which is this. And if we introduce the parameter values and calculate, we find that in this case it will be roughly 1.42 radians. So suppose now that we have a wheel contact point with a displacement, then that z is forced to move with 1 centimeter amplitude. The peak value is 1 centimeter at 3 Hertz. Then the car displacement will, at 3 Hertz, will of course be 5.4 times the phase factor here times the excitation at 3 Hertz. And the value, if we consider the root mean square value, since it's pure sine, we can simply divide the amplitude or peak value with the square root of 2, and we obtain 3.8 centimeters. So the car will oscillate with a higher amplitude than the road. So it will be an amplification along the path. The phase shift relative to the road is, as we saw before, 1.42 radians, and it's also possible to interpret this as a phase shift, because if we if you manipulate the exponent in the complex exponential here, we can see that we can interpret this phase angle here as a time shift. And the question now is, how is this time shift, how to illustrate it? Well, if we plot first the time dependence of the position of the wheel road contact point, and let us say now that we assume, or that we start the watch, so to speak, when it passes 0 here, so we get a pure sine. Then it turns out that the car displacement will also be a sine, of course, but with a different amplitude. And as you can see here, the sine shape here will be shifted along the time axis. And the magnitude of this time shift will be the phase angle over the angular frequency. And in this case, it's it will be shifted 75 milliseconds backward in time. If we instead now, on previous slides we have investigated the special case when the excitation is at 3 Hertz. If we plot the magnitude, that is the absolute value of the frequency response function versus frequency, as a function frequency, then we can see that we have a peak, a single peak here. And that is, of course, the resonance frequency. So at this particular frequency, slightly below 3 Hertz, we have maximum sensitivity in the system. So the absolute value of the frequency response function is at its max in this point. That can actually be used as a definition of the resonance frequency. The frequency where the frequency response function obtains a local maximum. The phase function looks like this, the phase angle. And as you can see, at the resonance frequency, we have a phase drop, a drastic phase drop. Without losses, it can be shown that the phase will drop pi radians exactly at the resonance frequency. But in this case, when we have losses, the drop will be smeared out sort of over a larger frequency interval.